We were discussing about the inversion. So in this case, you can see. So in this case, in the type of inversion, so you can see there's a lot of electrons here. So electron concentration is in this direction, but the field is not favorable. Okay, field oppose. So if there is a diffusion gradient, that means the electrons will try to flow in this direction. Okay, but the field opposes this electron flow. Okay, that is why the net current is equal to 0. Similarly, the holes here, the holes will also try to move in this direction, but the field opposes the flow of holes. Okay, that is why the net current is equal to 0. Now let us take one case. Okay, let's take one case. Okay, so this is let's concentrate on p-type semiconductor. Okay, so this is the inversion here. So this is a blown up image here. So you can see the EI. Okay, so this EI has gone below EF. Okay, it has gone by this amount. Okay. So this amount of the band bending, okay, at the surface, okay, that is for all psi s, okay, so that is the amount of the band bending. So you recall earlier we wrote Vg is equal to, what is that, Vfb plus Vox plus psi s, okay, so that this is the psi x, okay, so your Vg is causing this band bending, okay. Now we don't know how much is the band bending, okay, so for that we need to find out the relationship between Vg and psi s. So let's put some numbers of if the psi s, okay, if the psi s is equal to 2 phi f, okay, you remember this is q phi f, this is nothing but kt by q ln Na by Ni, right? So if the band bending is twice the amount of this value, that means this delta and this delta will be the same. Okay, so or it says that the amount of electrons at the surface is equal to amount of holes in the bulk, right? So we call that condition as like an inversion. Okay, so that is, okay, the surface is perfectly inverted. Okay, so the electron concentration. Okay, so the number of electrons. Okay, so n at surface equal to p at the bulk. Okay, so it is as much, so the surface is as much as it is n type as it as the bulk is a p type. So we are completely inverted the surface. Okay, suppose earlier it was like 10 to the power of 16 holes here. Suppose you convert, you have applied a bias such that the surface is now around 10 to the power of 16 electrons per centimeter cube. Okay, so that is the inversion condition. Now the question is, okay, so we briefly touched upon this question, okay, where does this charge come from? Okay, surface charge come from, because you look at this guy, if you do Ni square by P, okay, so that means only 10 to the power of 4 electrons here. And so if you wait for a lot of time, okay, that means, okay, so so you have only 10 to the power of 4 electrons, that's the concentration, but how do you get 10 to the power of 16? Okay, because this is a large number. Okay, now the question is, okay, where does this surface charge come from? In the case of accumulation, okay, in the case of accumulation, okay, so this is majority carriers. Okay, so here you may be increasing from 10 to the power of 16 to 10 to the power of 18 or something like this. Okay, this is not a big deal. Okay, and the material can always adjust. Okay, so there is something known as a dielectric relaxation time. Okay, so this is the amount of time it requires for the material to adjust for any carrier concentration. Okay, so this is something like RC time constant. In fact, this is exactly like an RC time. So this is sigma. Okay, sigma is equal to like 1 over rho. Okay, multiplied by the dielectric constant. Okay, so this is similar to an RC time constant. So you can assume it's like an RC time constant of any material. Okay, rather than RC, they are lumped values. Okay, they are capacitance and resistance of lumped components. Okay, but this is like, it depends upon the conductivity and it depends upon the dielectric constants. Okay, both this determines the RC values. So this is the dielectric relaxation time of any material. Okay, this is pretty fast. Okay, so this is like in picoseconds. Okay, 10 to the power of minus 12 seconds. Okay, so even if you apply the gate voltage very fast. Okay, so the substrate can adjust. Okay, so if you go, suppose you go from flat band to accumulation, you are switching the surface between flat band and accumulation, even like a terahertz or something like this one, it can adjust. But if you go to inversion, okay, inversion, your electrons are the minority carriers now. Okay, electrons are the minority carriers. So now it cannot adjust because you have only suppose like 10 to the power of 4, you have to go all the way from 10 to the power of 16. Okay, it's not. So now the question is, where does it come from? Okay, where does it come from? So it comes from something known as okay. So inside the material, okay, inside the material there are always trap levels. Okay, the trap levels are there. Okay, so one is thermal generation, and suppose there are traps. Okay, so you might have studied something known as Shockley-Reed-Hall method. Okay, so this is inside the band gap. Okay, so this is EI here. So there may be another additional levels here. These additional levels, this is trap levels which are closer to the EI. Okay, so this could be due to any material like a transition metals like iron, copper, nickel, all those they can create trap levels here. Okay, so these traps, what it does is that it can it can provide it acts like a generation recombination synthesis. Okay, so suppose there is an electron here and there is a hole here. Okay, so you might have studied about direct and indirect band gap semiconductors, right? So the silicon is an indirect band gap semiconductor. So if you have an electron here and a hole here, it cannot directly get recombined, right? So so otherwise we could have used silicon for light emitting devices. Okay, so since silicon is an indirect band gap semiconductor, okay, they can this recombination can happen only through these trap levels. So they can thermally recombine also, but the thermal recombination rates are very small. Okay, for example, your Ni is equal to 10 to the power of 10. Okay, that's it. That's the amount of electrons you can generate as well as recombine. Okay, so you can generate only 10 to the power of 10 electrons per centimeter cube by thermal generation. But through this SRH, okay, if you have trap level, depending upon the trap density, okay, so the SRH, this is an expression. I am not going for this one. Okay, so the generation recombination rate is like this one. Okay, so and all these time constants. Okay, it depends upon the number of traps and the position of the trap in the band gap. Okay, so you can, what I'm trying to say is that you can have more generation and recombination that is being predicted by the thermal values. Okay, so under thermodynamics, under a particular temperature, okay, it may give some generation recombination number, but you can exceed that number by having this trap level. Okay, so this amount of traps are carefully controlled. Okay, so if you have trap levels here, you can have more generation and recombination event. And also if there is a band bending, okay, so you can so in some cases you can have more recombination and you can have more less generation. In some cases you have more generation and you have less recombination. So when you change the surface condition from depletion to inversion, or so here you are trying to favor generation. Okay, so you are trying to favor generation, so there will be more generation, and this is supplying this electron for inversion. Okay, so in a MOS capacitor, so these electrons come from these events. Okay, so they are being generated inside. Okay, so the amount of generation depends again on the temperature and everything, but it is beyond whatever the thermal equilibrium values. Okay, it's beyond this 10 power 10. Okay, it is much higher than 10 power 10. So it is, but it takes some time. Okay, so this is a rate. Okay, so then you have to multiply by T. Okay, so you have to wait for some time. Okay, so so this is a rate, and so you multiply by the time you can wait. So this will give you the concentration. So let me repeat again. For accumulation, it's not a problem. Okay, you can, because these are majority carriers. But for inversion, these are minority carriers. Okay, so so this depends upon the rate at which the generation events are happening. Okay, and then you need to depending upon the rate. Okay, sometimes you can wait slow for a less amount of time. Sometimes if the rates are very small, you need to wait a lot of time to get enough number of carriers at the inversion. So this is again the same case here. So if the notation is like that. Okay, if the band bending is upward. Okay, if the band bending is upward, we call this ISS less than negative. Okay, so this is IS negative. IS. If the band bending is down, okay, so this is IS positive. Okay, that's a notation. Okay, so if the size is negative for accumulation, that is whenever it goes up in the. So this is a flat band case. This is the size is greater than 0. So this is size is positive. Now it is becoming positive here. This is so this is weak inversion. This is strong inversion. So that is this is So that means the amount of electrons at the surface is much higher than the holes in the bulk. Okay, we call it as a strong inversion. Now, so we were interested in the relationship between Vg and psi s. Okay, Vg and psi s. So you can actually solve a Poisson equation. Okay, Poisson equation it's a relationship between, okay, it relates between psi square phi and the q, whatever the q. Okay, so this is rho by epsilon actually, the relationship. So if you know the charge concentration, you can always find the potential distribution. Okay, so this is known as a Poisson equation. So the charge distribution and the potential, they are related. So if you know the charge distribution, you can always find the potential. Okay, but this is in our case. Okay, if so in space, if you have some collection of charges, then it is easier. But in this case, in our case, it is slightly complicated because del square phi is equal to, then there is a rho is actually a function of potential. Okay, so number of electrons and number of holes. Okay, it depends upon the amount of band bending. Okay, so solving this equation in a semiconductor, okay, it's not straightforward. Okay, but you can solve it. I'm not going through that analytical approach here. Okay, so this can be found in all the textbooks which I had mentioned. So what it shows, right? If you solve this equation and if you try to find this relationship, okay, so this is Vg is equal to Vfp plus If and Vox. So if you try to plot the surface potential versus the gate voltage, okay, so this is under your control. You are varying the gate voltage, so you can make it negative or you can make it positive. Now let us try to see how does the surface potential changes. Okay, surface potential. So you can see in this region, okay, surface potential more or less follows the gate voltage. Okay, so this is the depletion, and this condition is known as inversion, and this is accumulation. Okay, you can see even though you vary the gate voltage a lot, okay, so between here to here, okay, so you have only changing the surface voltage, surface potential by a small amount. That reason is and similarly the same thing with accumulation. Okay, it's not changing much. Okay, so we call this as like a pinning. Okay, so it is, even though we are changing the gate voltage a lot, but the surface potential hardly changes. Okay, so then this is constant. Okay, so then if this is pinned, that means, okay, so whatever the increase in gate voltage, okay, bulk of this burden is being taken by the oxide. Okay, so most of the extra whatever the extra applied voltage is being dropped across the oxide. That means the oxide field increases. Now let us understand why this is being pinned. Okay, this is being, so so if you are applying, so this is MOS. When you apply when you apply any bias, when you vary the bias at the metal, what is suppose you are changing by delta V. Essentially what you are doing is that you are changing the charge at that electrode. You are changing by delta Q. So the metal electrode is connected to a voltage supply. So you can easily increase or because the voltage supply can supply the charge. But that is not the case. So this delta Q at the metal should be equal to delta Q at the semiconductor. So the charge has to be balanced. But whenever this is increasing, okay, this has to follow the charge, okay, because the same amount of charge. Now under inversion and accumulation, okay, so whatever the carriers, the carrier concentration is exponentially proportional, because you can see it's proportional to the band bending. Because even if you vary the band bending as by little amount, the charge vary, because the electron and the hole concentration, right? It depends upon the relative position of the difference between the Fermi level and the bands. So under accumulation and inversion, right, the surface carrier concentration changes. Even if you change the band bending a little, even if you change the band bending a little, okay, the carrier concentration increases a lot, it increases exponentially. That is why even if you vary the gate voltage by a lot, okay, it requires the semiconductor by vary the surface potential by only a small amount. Okay, it can supply the same amount of charge. Okay, that is why it is pinned. Is that clear? So the pinning is coming from due to the exponential relationship between the band bending and the charge. But that is not present under depletion. Okay, we will see where are the charges and the depletion coming from. So in the depletion, in the depleted region, okay, so the surface band bending, okay, it follows more or less the gate voltage, because it is neither in accumulation, it is neither in inversion. So it cannot have this at exponential dependence. So as I said earlier, most of the extra voltage, okay, which is that is going to become being dropped across the oxide. Now let us do some try to get some analytical expressions in depletion. Okay, so in depletion, okay, now let us see whether we can get some relationship between the surface band bending and the gate voltage. Okay, so when we are being depleted, okay, what we are going to do is that we are going to assume that, okay, it is completely depleted of mobile carriers, or amount of charge, okay, amount of the electron or the hole concentration is very small. Okay, now but it's still the gate, okay, so the charge in the gate should be same as the charge in the semiconductor. Okay, now the question is, where does this charge come from? But for that you need to look at any semiconductor. You can always write the charge neutrality expression. Okay, so how does you write it? This is so this is let's slide LHS. This is the amount of electrons, and where is the negative charge come from? It comes from Na minus. Okay, this is the additional source of negative charge. So it should be equal to holes. So these are the positive charges and these are the negative charges. Then if there are no sufficient these carriers, okay, if there are no sufficient charges, okay, that means it has to come from either from Na minus or Nd plus. So in this case, okay, suppose let's assume that it has only one type of doping. Okay, so let's say if it is p type, so you have most of the charge it comes from Na minus. So when you vary the gate voltage, okay, so when you are varying the gate voltage, for example, in this case you are applying positive bias here. Okay, so the gate charge is positive. So the semiconductor has equal number of negative charges. Okay, semiconductor, so the G, the S should be negative. So the negative charges come from these acceptor atoms. Okay, so let's assume if it is a uniformly doped, okay, that means there is no dope, the doping is uniform. So you can always write rho is equal to minus Q times Na. Rho is the volume charge density, is equal to nothing but the electronic charge multiplied by the acceptor. Let's assume it is all are ionized. Okay, so it is Na. So this depletion, the surface depletion, okay, it extends to something known as a depletion width. So this is a W, okay, so it extends to W here. Okay, so this all charges, this is depletion charges. So you can think, okay, when you apply Vg here, okay, when you are increasing or decreasing, what is happening is that this is depletion width, okay, it is going to modulate the depletion width. So any extra increase in Vg, it puts extra charge at the gate electrode. Okay, so how does it come? Okay, what it does is that, okay, it increases the depletion width. Okay, so it increases the depletion width, it gets extra amount of charge. Okay, so that is why in the depletion region, okay, your surface potential is changing like this. Okay, it is following the gate bias, because any extra charge, it has to come from the depletion charge. So if you try to solve the Poisson equation, okay, in the depletion region, okay, the Poisson equation is very simple, okay, because this charge, okay, this is, so the right hand side is a constant, okay, you don't need to worry about electrons and holes, okay, so if it is electrons and holes, then you have all this exponential dependence come from, okay. So that is why we are taking this depletion approximation. We are neglecting the amount of the contribution from electrons and holes. That's a reasonable assumption. So if you do this one, so what you can do, so this dE by dx equal to this one. So you can do a first integration. So what it does is that, so this E is equal to minus Q Na by epsilon into x plus constant. Okay, so this is a constant of integration. So what you can do is that this constant of integration you put at x equal to W. At x equal to W means that's the edge of the depletion region. That's the edge of the depletion region, that is, so somewhere here. Okay, so it's somewhere here. This is the edge of the depletion region. So after that, so there is the bands are flat. Okay, the bands are flat. Okay, that means there is no electric field. So that is the boundary condition we are assuming. So we will assume at x equal to W, E is equal to 0. So if you put that one, okay, so you can get, so at x equal to W, you can get this relationship. Okay, so this is valid. So you can see the electric field, okay, it varies. Okay, it varies. So at x equal to 0, the field is maximum. So that means at the interface, the field is maximum, the field is highest at the interface. Okay, then the field reduces, okay, and it becomes 0 at the bulk. So if you have the electric field, you can calculate the electrostatic potential, because the field and potentials are related. Okay, so field is nothing but d psi by dx, right? So you can do one more integration. Okay, one more integration. So then you can find the potential and this one. So if we at x equal to w, okay, if you know the x equal to w, you can find the surface band bending. Okay, so this looks similar. This looks similar to your PN junction. Okay, you can see it is more or less similar here. Okay, w is proportional to psi s. Okay, so in the case of PN junction, you have this built-in potential here. Okay, and in the case of QNA, okay, you had this contribution from both sides, QNA and ND. Okay, so you had something like in the denominator, what you had is a NA ND by Na plus Nd. So here you have, so it's a depletion region. So here there is only constant contribution from Na. That's the main difference. Okay, so this is something you have to keep in mind. So this is the difference between the depletion region in a MOS capacitor and the depletion region in a PN junction diode. So if you try to plot, okay, let's try to plot. So the field is maximum here. Then the field reduces and it becomes 0 at the depletion width, and it becomes 0 here, because this is a quasi-neutral region. This is a neutral region here. But at the but if you try to move from semiconductor to oxide, this is oxide here. Okay, there is a jump here. Okay, there is a jump here. So this jump, okay, it is caused by, there is a, you can see this is epsilon ox here, this is epsilon silicon here. Okay, so the field, if you the field should be equal to epsilon Si ESI. So this, whatever they in, so you can see the epsilon silicon. Okay, this epsilon silicon is roughly it's around 11.7. This is 3.9 multiplied by ESI. So this is roughly 3 times ESI. So the field inside the oxide is roughly 3 times the silicon. So that is why from there is jump from this value to this value. Okay, so there is nothing unusual here. Okay, it is all predicted by the electrostatics. Okay, so the field increases from semiconductor to the oxide, and then the field is constant inside the oxide. Okay, that is because the Q is equal to 0 here. Okay, we assume it's an ideal insulator. There are no charges. Okay, there are no trapped or there are no charges inside this insulator. The Q is equal to 0. The field is equal to 0. Field equal to 0. So the field remains. Sorry, Q is equal to field remains constant. Okay, field remains constant. And then at D, okay, so this is oxide here, this is again metal here, metal or polysilicon, the field goes to 0 here, because it's a perfect conductor here. And from this from field, if you go to potential, okay, from field to potential, what is being happening is that, okay, so here you have this parabolic relationship. So because this is a linear, okay, so this is a linear, you are doing an integration, you get a parabolic relationship for electrostatic potential inside the semiconductor. But inside the oxide, here it was constant. Okay, it becomes linear here. Okay, so the electrostatic potential varies linearly inside the insulator or the oxide. Then when it hits this metal, okay, it is constant there. Okay, this is whatever the Vg or whatever this one. So, but you can see here inside along the dielectric interface. Okay, the dielectric interface, there is no discontinuity in the electrostatic potential. Okay, you see the discontinuity only in the electric field, not in the electrostatic potential. So this is a simple electric field. Okay, so the electrostatic potential. Once you know the electrostatic potential, you can always draw the energy band diagram. Okay, so the energy, because energy is equal to nothing but Q times V of X, right? So only different. Okay, so this is true for a homogeneous material. Okay, if you have a homogeneous material like both sides, say silicon in the case of a PN junction, but what here it is in a heterogeneous system. Okay, it's a heterogeneous system. So if you want to write E, so it becomes so it is Q of V of X plus whatever the delta EC you have to write. Okay, because when you change from one material to another material, there could be discontinuities in EC or EV. So at the material discontinuities, you need to add these numbers. Okay, whether it is going from silicon to oxide or from oxide to metal, you need to add these numbers. Okay, so once you have this one, okay, so your potential was something like this one. So that is why you get these discontinuities. So only thing is that if you look at this one, okay, this is the exactly inverse of this one. You go invert and plus add delta EC. That's how you get the energy band diagram. So all you need to do is that, so if you have a charge distribution, okay, you solve the Poisson's equation, and then you get, okay, so this will give you psi, then you invert psi, you plot minus psi, then apply Q here and plus whatever the delta EC, whatever the discontinuities which are coming from the material. So that will give you the band diagrams. Now let's try whether we can find a voltage drop if you want to try to estimate the voltage drop. So now we know qualitatively how to draw the energy band diagram, and we know how we saw how much is the band bending inside the semiconductor. Okay, now the first the question is, okay, how do you calculate the voltage drop? So for that, if you want to calculate the voltage drop, okay, so this is also similar. So from the Gauss's law, you can always write epsilon. Okay, you take any what it says is that if you have any Gauss volume here, okay, whatever the charge, whatever the electric field here is related to Q. So if you want to try to find the now the question is, okay, so we were trying to, so our goal is to find the relationship. We saw that Vg is equal to Vox plus psi s plus VFD. Okay, so we know VFD, we found a way to find psi s. Now the question is, how do you find Vox? Okay, so in order to calculate the potential, the voltage drop inside the insulator, okay, what do you need to do? So we know that, okay, inside the oxide, there is no, there are no charges, okay, and we from ESI we know Eox. Okay, so if we know Eox, okay, we can find Vox. Okay, Vox is nothing but Vox by Tox, basically Eox. Right. Now so this is a, so all you need to write is, okay, this Eox is nothing but Eox into Tox plus psi s plus VFT, and this Eox is related to the semiconductor field through the depletion charge. So if you know the depletion charge, okay, if you know the depletion charge, you can find the field. So that is nothing but, okay, if you have some depletion charge here, the electric field is nothing but the Q depletion over epsilon, this one. So the depletion charge is nothing but, because it's a uniformly doped material, the depletion charge is nothing but Q Na times W, where W is the width of the depletion region. So this is a depletion charge. So now now you have this one, okay, so the entire Vg, okay, Vg is equal to VFV. So we found out this one, this is a constant, okay, we found out the psi s, and this is a Vox. Okay, Vox is nothing but Q times the depletion by epsilon of SiO2, okay, this one. So now you see this Vg is related to psi s, and the psi s comes in this term also, the depletion charge. Okay, so when you vary Vg, what is happening is that you are varying the psi s. The psi s varies the depletion charge also. Okay, that intention. So you can see the psi s. Okay, so that is why the Vg and the psi s. Okay, it's not a linear relationship. Okay, the linear, there is only this term and this term is coming. So the entire Vg is not contributed to increasing or decreasing the size. Okay, it is partially given for this depletion charge. Okay, so keep in mind this is valid only for depletion region, because we have neglected the contribution from the other carriers, the electrons and the holes. So in depletion region, okay, in depletion region this relationship is valid, the Vg and the Vf. If you need a relationship between Vg and psi s in the accumulation or inversion, you need to go back to the Poisson's equation, okay, and you need to solve the Poisson equation by taking the electron and the hole contribution into account. So that is given in the normal textbooks like Pierre and all, it is given, but the expressions are lengthy.